Hi, I'm Martin. I'm a research and development engineer at Kitware, and I'm talking about CMake Instrumentation, which is this new CMake feature, which is intended to provide data about the timing and performance of your builds and tests, and hopefully provide that in a way which is useful, and you can make decisions to create performance improvements for your CMake projects. Just a quick overview. I'm just going to be talking about what is this new CMake Instrumentation feature, how to enable it, how to use that data to hopefully make improvements to your projects, and then some of the future things that are currently in development. So what is CMake Instrumentation? I have a little quote here from the documentation, but it's an API to allow the collection of timing data, target information, and system diagnostic information during the configure, generate, build, test, and install steps for your CMake projects. And the goal of it is to really answer a couple of questions, which are how long does it take for my project to configure, build, test, install, and then why does it take so long? So this is an example of running a build without instrumentation, and you might have a little bit of output. Maybe depending on the project, there might be a lot more than this because you might have a spam of compiler warnings or something, but probably not a lot of useful data to show you why your build is taking as long as it is. And for a big project, like with thousands of targets like this, it might be sitting there for half an hour and you have no insight as to why it's taking so long or how to make improvements. So then with instrumentation, this is one of the things you can do is generate a Google Trace event visualization. So this is a visualization of the Trilunos build, but you can see here at the beginning, there's like the configure and generate from CMake, and then this pretty highly parallel build, and you can see exactly which compile, link, custom commands are happening when and how long they take. So just sort of a high-level overview of how this works during your build. CMake will generate instrumentation data. It does this by wrapping every command in a launcher, and it writes these snippet files to a directory in your build tree. And so there'll be one snippet file for each command, like each compile or link. And then to prevent these from just accruing indefinitely or being really hard to look at, because you would just have this directory which is growing with more and more data, we have a process called indexing, which takes all the generated instrumentation data and creates an index of it. And you can configure when that happens, and then the CMake will pass the index file to user-written callbacks, which can parse this instrumentation data or send it to a database or do anything else, and then CMake will automatically clean up the generated files. So here's just a look at what those snippet files look like. So for every, like the overall CMake configure, generate, build, but also for individual compile, link, custom commands, tests, it will generate some JSON output showing some of the data from that invocation. That's data including like the time that it started at, how long it ran for, the type of command, the outputs and the output sizes on disk, and then some system information about the CPU load average and host memory usage before and after the command was run, and then some other things as well. And then for indexing, creates an index file that will just list a list of all of the snippet files that are associated with it. And it's customizable. You can specify hooks, which are when you want this indexing process to occur. So you can set it up to happen after every build or after every invocation of CTest or something else. You can also run the indexing manually. And then you can specify callbacks, which are just user-written scripts to process the instrumentation data. And because you can have these arbitrary scripts that run automatically at certain points in your CMake build, it's very flexible what you can do. I have an example here. On my development machine, I set up a instrumentation query so that whenever any build finishes on my machine, it will send me a desktop notification saying the build finished and it succeeded and this is how long it took. And that will have access to all of the instrumentation data, so you can do a lot with that. So just a brief explanation of how to actually enable this. There's a CMake instrumentation command that you can put in your project's CMake lists to define basically an instrumentation query for the specific project. You'll give it like a version, which right now is just always going to be 1, but that's to provide future proofing. And then there's some optional arguments. You can tell it to collect additional data about the system, to generate a Google Trace visualization, or to submit data to CDash. You can specify which hooks you want to enable to run the indexing, and then whatever your callback function is. And then similarly to that, you can also have user-level queries. So by default, these would go in your like on Linux, it would be your .config CMake directory, but it's configurable and it's different for different architectures. But this is a very similar query, but it's in a JSON format, and you can put a file in that location, and then all of your CMake builds will have instrumentation enabled with these options. And then lastly, there's an environment level enablement where if you don't want to do any custom scripts to handle your data, but you just want to submit it to CDash, you can set this environment variable, and it will just automatically create a very minimal instrumentation query, which just says, I want the system information, and I want to submit my data to CDash. So this is kind of recap. I just wanted to put all of the options on one slide. These are basically how you can configure instrumentation. There's the different hooks of when you want the indexing to occur, the optional data that you want to do, that you want to collect, and then your callbacks. And here's an example using the CDash dashboard. This is of CMake's own build. This is one of the nightly pipelines. We submit instrumentation data. So every night you can see on CDash what the actual build process looked like in the visualization view on CDash. So now I'm going to talk a little bit about some of the practical uses of how you can take this data and act on it. So from my perspective, there's kind of two main use cases. One is just to collect data once for a single build and then analyze the outputs and see if you can gain any insights or identify bottlenecks in the performance or test incremental improvements. And then the other would be to collect data across many builds. So this is where enabling it on a project or on a user scope can be helpful. You can track performance over time, not only like the overall time, but also you could track performance of our individual targets taking longer to build after some diff. And you could do this on like a CI machine, or you could do it if you have like many developers sharing development space. You can track everyone's CMake builds and see how much time are people waiting on things and how much resources are being allocated to builds, and make budgeting information decisions and things like that based on the data. And some of the kinds of questions you could try to answer with instrumentation are, what are the primary performance bottlenecks? How much would my build benefit from greater parallelization? And how do things like the toolchain and the environment and the cache options affect the performance? So I have an example here of just how having like a visual of the actual build process can be helpful to make informed improvements. So sometimes you might have something that looks kind of like this, where you'll have gaps in the parallelization. Here there's a compilation target which is blocked by some dependencies. This can happen if you have like a lot of code generation or a few other things. But so you might want to see that if your code generation is a major bottleneck, then that becomes a place that you can look to optimize. Maybe you cache the outputs of that or something. There's also this optimize dependencies option in CMake, which you can use to relax some of the dependencies, the compile time dependencies for static and object libraries. So if you're seeing some of these gaps, depending on what your build looks like, that might be an option to help improve. And then here's some ways you can improve the test and install performance just by looking at some of the visual data. Starting in CMake 330, you can do the install step in parallel. So if you have a really big project that has a install step that's being run as part of a common developer workflow, then you might want to enable that. But it is parallel at the directory level. So if you have a really big directory, then it's not going to parallelize very well. You can see an example here where this is an installation for a large project, and there's one directory that is way bigger than the rest. And so the whole even though it's parallel, the entire timing for the installation step is bottlenecked on that one directory. And similarly with C-test, if you have many tests which are all 10 seconds, but then one test which is 20 minutes, then your overall test time is going to be at least 20 minutes. And being able to sort of visualize what that looks like can help you decide, maybe I should split up this test into multiple subtests or something. So another example of some ways you can use this data. This is from a project where we compared the tool chains and the link performance. So running 2 different builds with instrumentation and then summing up all of the total link time across all of the snippets and comparing the GNU linker with the LLVM and seeing how much total CPU time is being spent linking for each of those. Could also do something where you sum up the total time spent for building different targets and figure out which of your build targets are having the highest impact on the build time. So just a sort of history and where it is right now. So starting in CMake 4.0 is when instrumentation is available, but it's an experimental feature, and there's a bit of work you have to do to enable it. It's going to be starting in 4.3, which is coming out now, where the experimental gating is dropped, and so it's just a standard feature that you can use. and there's continued work being done in future versions. These are some of the features that are currently being worked on. There's outputting the standard out and standard error of the commands, which could be used for a bunch of things, but the motivating use case was to identify cache hits so we can differentiate compiled data, this was copied from a cache versus this is actually being compiled. Integration with the Clang time trace, which provides more detailed insight into what the compile time actually looks like, and then collecting process metrics, which would be especially helpful for like tests, but allows you to get things like the total memory usage by one test or build process, and you can use that to track performance regressions in the memory usage of your tests. So it's just some links here. There's a blog post about this on kitware.org/blog, and also the documentation on cmake.org/cmake. So if you have any, you want to look into this more, you can find resources there. So that's all I have. Is there any questions? Yeah.
Okay, great. I like the project a lot. I think one thing that I've experienced on CMake builds recently that's really valuable here is a measure of sleep state when building on different file systems. You see the file system actually bottlenecking the yield. That it's just the kernel going to sleep and running the clock out as it waits for the business to catch up. But otherwise, I think a ton of value.
Okay, yep, thanks. Yep.
So first of all, this is really nice. I really like this feature. And also, I wanted to ask whether you've experimented with integrating with like compiler time tracing, like for example, like time trace.
That is actually one of the things that was on the slide, the Clang time trace integration. So yeah, that's one of the future things that we're looking at adding. Yep. Yep.
I'd like to integrate this data with another monitoring system.
There's no like integration with other tools, but the way it's set up is you can write arbitrary callback scripts, which are just passed all of the data. So then if you want to submit it to some database or something, then you can just write a script to take in the data and convert the format to whatever you need. Yep.
So if I get it right, the way you use it is like some command in your CMake files.
There's a few different ways to enable it. So one would be to add it as a command in your CMake file. You can also just use a JSON-based query, which could be set for the user so that all of your CMake projects will have the same instrumentation query. You can also put this file inside of the build tree, which is a little bit more manual, but you could set up a file-based query that way.
I was going to ask whether you had some quick way that you could configure option, Clang ID, or no, this is
Yeah, so this will enable instrumentation just with an environment variable. The thing about this is that if you wanted to have any kind of custom script which will parse the data, there's no way to just set that up with an environment variable, so this won't be able to do that. The only thing this will do with the data is submit it to CDash. So if you're using CDash to look at the data, you can use this.
we can talk later.
Sure.
I would love to have it. We want to configure dash enable that thing with the options. Just the same way you generate compile command.
Yeah, we can talk after. I have some thoughts about that. But. Yeah.
I have a little more knowledge of what this was created for, so I think it's worth mentioning that this could be set up if you have like a large team working on a project. Say you've got 100 engineers working on the same project, and you could set it up such that it was going to some central repository database, and then like the developer's like, this build is really slow, I'm always spending time. You actually can like point at, no, like on average, it's taking everybody 3 minutes to build this package. Or maybe you just discover in there that, yeah, there are a few anomalies, like the one guy that's like, this thing always takes forever for me. And discover in the database that, yeah, there's a couple people that for some reason, whatever machines they're using are causing trouble. So I think you could put this easily into a broader monitoring system for a larger heterogeneous development platform. And then you you got these callbacks, so it's very configurable.
Even automatically resizing. So when we talk about resizing the host, the allocation of resources, processing, actual data.
I think, John, what you're working on, trying to get this enabled in spec?
Yeah, you can implement spec environments.
So when you dispatch to CDash, right, is there any of this visualization stuff, or that only works via the trace?
Yeah, this is visualization in CDash. So
So that's already integrated
Yeah.
into CDash.
all right, thank you.